We are recording. Let's knock this one out of the park. We got Unit 1, Lesson 5 here, Inequalities. To talk about inequalities, though, right, we are looking at an expression. For example, this first one right here, x is less than 3. There are multiple answers. Right? -1 is less than 3. -47 is less than 3. -1 billion is less than 3. So there are multiple answers. We need a way to notate this, Mrs. Contreras. So we need to establish how we can, in the future, give the answer when there are multiple answers, when there's an infinite amount of multiple answers. So on the number line, where are the answers x is less than 3?
Well, it doesn't include 3, so we need an open circle there. And then we need all of the numbers that are less than 3, so that's everything to the left.
All right, so we got all of the integers here.
Oh, but I said all the numbers. All the real numbers.
All the real numbers. All right, so like 2.5, right?
2.5, yeah.
We don't know E yet. All right, all these numbers, right?
Right? But infinitely close to 3, so we can get up to where the 3 is, but we can't include 3.
All right. Oh, there's a graph. There's a well, I guess it'd be, what is that? One-dimensional graph. There's one dimension, right? Yeah, there's like an x coordinate, no y coordinate. We have a graph here. Right? We do not expect you to draw a graph of your answers every single time. We have a notation for all the numbers less than 3. And the way we do it is we use an open parenthesis to describe that we want to go all the way up to 3. Right? And how low do we want to go?
Can we go down low, all the way to the floor?
Like you never stop? Okay,
let's bring it to the top. That's I think the next question. When negative infinity, that's like
negative infinity. Here we go. This is how I write my infinities.
All the way to the end. Ooh, that is cringy.
Yeah. Negative infinity to 3. All the numbers from negative infinity to 3 are valid in this inequality. This is how we write this. Let me proceed, though. If we are also including that number, so in this second example, if we're also including 5, we have a way for writing this. So all the numbers that are greater than 5, including 5, we're going to put a dot there, a filled-in circle. But what we want to do here is we want to go up to positive infinity, but we want to include the number 5. So we're going to use a different notation. We're going to use a bracket. Okay, so all the numbers, including 5, to infinity. We're going to use a bracket. All right, so if I want to say -6 to, from all the numbers between -6 and 7, including 7, but not including 6, how would I write that?
We need an open parenthesis, open, -6, comma, 7, and then close bracket, square thingy.
Yeah, I think we should call it a bracket, right? Parenthesis and bracket. I think that's all.
Parenthesis and bracket.
Right?
Parenthesis.
If I want to graph this on a one-dimensional graph here, this number line, I'm going to go ahead and
open circle on -6.
Yep.
Close circle on 7, and color in everything in between.
Get that sweet Blazer Pride red.
Ah, yes.
Ah, yes.
Go Blair.
Go Blair. Go Blazers. Blazer Pride.
Go Blazers.
All right, cool. So we got that. And then how about, just for clarity's sake, how are we going to do this?
Well, there's an or, so that makes me think that we have 2 intervals that we're going to need to talk about.
Excellent.
Maybe we should do the picture first before we get tangled up with the fancy interval notation.
Sweet. So let's include -3.
Okay, close circle on -3, and then everything to the left of -3, because x is less than or equal to -3.
All right, or
open circle on 0.
Okay.
And then all the numbers to the right of 0, because those are the greater numbers.
Excellent. And then what do you want to do for interval notation?
So I think we need to use the union symbol.
Because we want to take 2 sets and group them together.
Mm-hmm.
So let's go ahead and put a union. Just a big old U. A capital. It's not even a capital U. It's like a weird, like, you'll see it in future assignments. I'm not
It's
gonna.
a U, but then it doesn't have the little tail in it, so it's a different U.
And then we want to group these two things, so we're going to go from negative infinity to -3, and then how do I want to notate this 3?
Bracket.
Bracket. And then we want to go from 0, we don't want to include 0, up to infinity. And once again, I do apologize how I write infinities. One last thing before we proceed. How do you feel about this set?
And I don't know if that's ever possible. Because look where the arrows are going. They're going in completely opposite directions and no overlap of where those arrows are.
Mm-hmm.
So
right.
There is no number that I can think of, at least, that satisfies both of those inequalities. So our response for that would need to be something like the shrug guy, or
I don't know how to draw that. It's like something like that. I don't know. That's bad.
Yeah, sure.
we have a name for this group. We have a name for this set. We call it the empty set. You can use this little Greek symbol called a phi or a phi, not a faux or a thumb. A phi, right? That just means empty set. Or there's other ways you can describe that. We'll talk about that later. How about this set? Just while we're at it, how about less than or equal to 3 and greater than 0? How do you feel about that?
Well, that I think is entirely possible, because if you have, like, say, 1 works with that. Equal to 3 and 1 is greater than 0.
Mm-hmm.
And actually, if you take all the numbers between 0 and 3, that would still work. But then, can we include 0?
I don't think so, because we are strictly greater than, and we can include 3, right? Because we are less than or equal to 3, so we can go ahead and include that. I'm gonna throw some more symbols at you. I'm gonna go ahead and put an X, and this is a set of numbers. So we have a symbol in math that exemplifies this. It's a little E-looking thing, right? X is contained in the set 0 to 3, right? Not super important if you use this, everyone, but just for those who want to use it, we can also say that X is contained in the set of 0 to 3. That's what this string of symbols
say that's X is an element of the interval from 0 to 3. Is that another way of saying that?
Yeah. Mm-hmm. And in fact, I think what you're saying might be a little bit more proper. Right? The word contain might be used more for sets within other sets, but we'll get into that later. I like what you said better. Plus, it's an easy way to remember to draw an E, because element starts with E. Cool.
I think that's got a commie shortcut.
If you want to write that symbol, you do /element.
I think so.
Or maybe like ELEM.
Possibly just /in.
Oh, in. Okay, it's element in the set. Okay.
Oh, we could be totally wrong, because I'm just going based off of overleaf.
Yeah. We're still learning too. What the point of this first page, everyone, is we are going to use this notation to answer the following questions. Right? We are going to solve inequalities that are much more complicated than that first page. If I said, hey, for what values of X are greater than 3, the answer is quite simple. But for what values of X is X squared minus 6X plus 5 greater than or equal to 0? That's a more complicated answer. So what I want to do, Mrs. Contreras, is I actually want to take this. X squared minus 6X plus 5 is greater than or equal to 0. I'm going to go ahead and graph the left-hand side in Desmos. Hopefully I can get it up. Sweet. We got Desmos here. We got X squared. And then what was the rest of the expression? You know, I've already forgotten.
Minus 6X.
Minus 6X.
Plus 5.
Plus 5.
Oh, that's an 8, not a 6.
I'll fix that in just 1 second. We got let's put a 6. Boom. Changed it a little bit. All right. For what values of X is the horizontal input, is this graph, oops, oh, there's my background. I've lost my OneNote.
Oh no.
That's not good.
Should we pause the recording?
Yeah, let's pause. In a second, you will see us in a different location. All right, so we got this graph here, and we can now navigate back to OneNote. Cool, so I can draw. So we got x squared minus 6x plus 5 is greater than 0. When is this graph greater than 0?
It's wherever the parabola is like pointing. Because the only time that the graph is less than 0 is whenever the parabola is below the x-axis. And isn't that, those are also the roots?
Right, yeah, we got 1 and we got 5. Let's go back to this thing. Right? If we factor x plus, what do we got? What do we got to do here? We got x
I think minus and minus. Yeah.
There
X
we go.
minus 1, x minus 5.
Yeah. It's greater than or equal to 0. Right? We have x minus 1, x minus 5. 1 and 5 are when this thing is equal to 0. And we want when it's on the outside of those two values. Right? There is an alternate way to do this problem than to bring up Desmos every single time and look at the graph. And that is, let's draw a one-dimensional graph. I'm going to go ahead and give myself, not the straightest line. I'm going to give myself a number line. And I'm going to put those critical points on this number line. Right, I'm going to go, and I want to put them in order. So I'm going to put a 1 and then a 5. Right. What we can do is if we look at this graph is smooth. Right? It is precisely when the graph is 0 that it goes from positive to negative, and then from negative back to positive. So if I go back to this one-dimensional graph, if I can establish when this graph is positive, I know that at 1 it's going to become negative, and at 5 it's going to become positive. What happens when I plug in like a number less than 1 into this expression?
Like 0?
Yeah, let's plug in 0. That's a very easy number to work with. 0 minus 1, that's negative 1. I'm actually going to put a negative there. And then a 0 minus negative 5, that's negative 5. That's another negative. Negative times a negative, that's a positive. Right? This graph is positive for all the values before 1. That must be true because if there was any values less than 1 that were negative, then this graph would need to cross the x-axis again. But if it did that, then we'd have another 0. But 1 and 5 are the only zeros. So every value to the left of 1 must be positive because one of the values to the left of 1 is positive. And it's at 1 that we switch to negative. Don't believe me? Plug something in. Let's plug in 2. 2 minus 1 is 2. Sorry, 2 minus 1 is 1.
Positive 1.
Yeah, positive 1. 2 minus 1 is positive 1. 2 minus 5 is negative 3. So negative 3 times a negative number times a positive number, that is negative. And then same on a bigger than 5. Let's plug in a really big number, the biggest number I know. Let's go with 100. 99 times 95. I don't really care what it is. I just know that it's positive. And then no number to the right of 5 will be negative. Because in order for this graph to become negative, it would need to cross 0 again. But this does not cross 0 again, because then it would have a factor up here. So this graph here, very easy graph to produce, tells us the answer. When is x minus 1 times x minus 5 greater than or equal to 0? All these values and all these values. Do I include 1 and 5, Mrs. Contreras?
Heck yeah, because those are zeros. And we have that expression is greater than or equal to 0.
Yeah, or equal. So this is not how I want you to answer this question. I want you to provide to me the answer in interval notation. So x is an element of what interval notation?
Negative infinity, parentheses, negative infinity, comma, 1 bracket.
I'm going to try to do infinity the normal way.
Wow.
That wasn't that bad.
Look at
Negative infinity to 1.
1 bracket.
Bracket we included. Union.
Bracket 5, comma, infinity parentheses.
I'd rather just draw 2 circles, to be honest.
That was great.
There's an answer.
Wonderful. Keep trying, Mr. Kirk.
All right, so we're going to go down here. We're going to go ahead and give ourselves a graph. We're going to go ahead and put 1 and 5 on it. Cool. Plug 1 and 5. We're going to get positive, negative, positive. And then the answer ends up being what? What?
Whoa.
What?
The only reason we could do that before was because we were looking at roots, because we were looking, like 0 was what we were working with for our comparison. So now we have this x minus 5 times x minus 1, which is a parabola, I agree. But now it's looking at when that's less than or equal to 21. So we're looking at when that parabola is less than like a horizontal line up at 21, which is up here, out of the frame.
It's a really hard answer to question. That's a really hard answer to question. A really hard question to answer. Finding out when something's 21, because like
you need to like
21 product property, right?
True.
If I like the power of the 0 product property tells us that one of them must be 0, but for the 21 product property, there's like the numbers can be anything. All right, so we need to turn this into a 0 product property problem. What do you want to do?
Subtract.
Let's subtract.
We should take away 21 from both sides. Probably expand. Probably need to expand that also.
Let's do that. Let's move, and this is the most important thing I think that we can impart on everyone is that when solving inequalities, move everything to the left-hand side or the right-hand side. Let me not forget about the right-hand side, but move everything to one side and leave the other side with a 0, so we can use the 0 product property. All right, so let's go ahead and expand this thing. We can do x squared minus, correct me if I'm wrong, 6x plus 5 minus 21. Hopefully the same factors. X minus 6x, 5 minus 21, that's 4 minus 20. That's negative 16. Hopefully I'm right. And then let's see, we can, 16, I'm feeling 8 and 2.
Yeah, 8 and 2 sounds good.
8 and 2, and I want the negative 8 and the positive 2 because I want a negative 6. Look at that. That is the important points. Those are the important points. There's the correct grammar. Those are the important points. We're going to throw negative 2 and 8 onto a number line. And then now let's critically think about when these intervals are positive and negative. So how can I establish what this graph looks like over here?
Well, we have 8. We have x minus 8 times x 2, which we know is going to be a parabola. We know it's going to be a parabola facing upwards also. So that's helpful.
Yeah, so we don't we know without plugging anything in that this is going to go positive, negative, positive?
That's what we intuit, yes.
Yeah.
But
how can we
probably try just it.
Yeah.
Plug in some numbers. So like the most negative number that you know, negative
7.
87.
87.
Okay.
All right, negative 87 minus negative 8, that's negative 95. Negative 87 plus 2, that's negative 85. Do I need to calculate negative 95 times negative 85?
No, just use the signs.
Yeah.
Negative times negative is positive.
Boom. And you can imagine how this might be difficult when we add a lot more factors. Right? Positive, positive, negative, positive, negative, negative, positive. So all you got to do is keep track of the positives and negatives. All right. What I often tend to do is before I write the positive symbol, my computer was freaking out there for a second. I like to put a negative. I'll put a negative, and I'll kind of keep track of the negatives and positives based on the factors, and then combine them all at the end to get my final answer plus. All right. If I plug in what's a convenient number between negative 2 and 8?
0.
I agree. 0 is like the best number that you can work with in these problems. So 0, we're going to get negative. We're going to get a negative from the minus 8 and a positive, and those two things combined give me a negative. And then we can do the same thing with like a big number like 11. 11's huge.
So big.
Negative 3, sorry, not negative 3, positive 3 plus, and we got a positive 13, positive, positive. That's going to be a positive. So it is it's our intuition said it was an opening up parabola, and this is what was going to happen, but we also verified just with 2 calculations. Always good to look at a problem in 2 different ways.
Like this way and then this way.
All right, we got 9x cubed minus 6x squared plus x is greater than 0. Oh wait, we didn't finish this problem. We didn't finish this problem. Let's get the answer real quick.
Yes, interval notation.
Yeah. All right? We want to know when it's
Negative.
less than 0. When is this inequality less than 0?
From -2 to 8, and including both of those.
Yeah, let's go ahead and add this to our graph. It doesn't hurt. All right, and we're going to have -2 to 8. So this problem's a little bit different. We're not looking for when it's positive. We're looking for when it's negative. We need to verify what we're actually looking for. All right, now let's proceed. Sorry about that, everyone. Okay.
Oh, and if we were nervous about that, just to go back one more time, if
Yeah.
we were nervous about that, we could take a number between -2 and 8 and plug it back into our original inequality.
All right, let's
and
do
see if that's true.
let's do 5.
Okay, 5 sounds good.
All right, 5 minus 5 is
0. Okay, 0. Cool,
yeah,
we're good.
Ha 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 ha. That's why I picked 5. Got him. All right, let's look at this one. I think we have exhausted all the thought that can happen with number 2.
All right. There is a GCF.
Let's knock that GCF out. So let's take that x out. We got 9x squared minus 6x plus 1. Oh.
9 and 1. Those are perfect squares. So that makes me think that this might be a
Perfect square trinomial. Okay. Perfect square trinomials. We're going to have a 3x and a 1. And we don't want that to be a plus, so we want it to be a minus 1.
We want a negative, yeah.
Yeah, because when we square this, we're going to get 9x squared. Perfect. We're going to get positive 1. Perfect. We're going to get a negative 3x and another negative 3x. We got a perfect square trinomial.
Perfect.
Okay. Let's throw our roots on a number line.
What are we? 0 and
0.
1/3?
And then, yeah, 1/3. And if, let me not put that behind the 0. Let me put it in front of the 0. You know what? While I'm at it, I'm going to just move that over a little bit. Just for myself. Cool. All right. Let's go ahead and plug some stuff in. Let's plug in -5.
Negative times. Hey, wait, we have something that's being squared.
Yes, that's always going to be positive, right?
Yeah, well, always non-negative.
Always non-negative.
0, right?
When is it 0?
At 1/3.
Yeah, 1/3 and 0, right? So, at 1/3 in this case, yeah. So we've already accounted for that. So we got a negative and a positive. That's going to give us a negative.
Mm-hmm.
And then between 0 and 1/3, let's go with like 1/1000th.
Okay, so that's a positive number times something that's always non-negative, so it's still positive.
Positive. Cool, that becomes positive. And then how about something bigger than 1/3, like
2/3.
1 million? Oh, that works too.
We
1
got
million.
positive.
2/3 times 2/3 is positive. And then no matter what we plug in here, it's going to be positive. We're going to get positive. Look at that.
Interesting.
Negative, positive. Do you know what's happening graphically here?
I think we're doing like a bump that what do we call it? It has a
I would probably just say it touches the x-axis and then turns around.
Okay.
You wanted to use like some technical term?
I thought that there was a word for it, but
A double root?
Double root.
Double root. Yeah. This root 1/3 is happening twice. So it's almost like you cross through and cross through again, but both those crosses are happening at the same time. So it's touching the x-axis and then just turning around and getting out of there. Let's look at it real quick.
It's like the graph that changes its mind.
We got 3x cubed, right?
3x cubed?
What was it? I'm already forgetting.
We have 9x cubed.
9x cubed minus 6x squared minus, okay, so yeah, let's fix that. 9, that's a 0. 9 and 0, right next to each other. Minus 6x squared, and there was a plus x.
Plus x is
Let's zoom in on this thing. And exactly what we thought. Right?
Whoa.
We crossed throughout that single root, but when we have that double root, that square, it turns around. What do you think would happen if, like, let me go ahead and write this as how we factored it. What was it? It was
3x minus 1.
Minus 1, quantity squared.
Indeed.
Yeah. What do you think is going to happen if I make that a 3?
Oh, I think it might change because then the parity like the even or oddness, that changes when we take that and we make it a 3 instead. So then the signs are going to matter because
right? When it's odd, like we're still crossing at 0, but when it's odd, right, now negative and positive numbers do matter. Like before, when it was squared, when you square something, it's always positive. But when it's cubed, the output can be positive or negative. So it will change sign when you pass 1/3. It's going to go from positive to negative or negative to positive. So that number matters. When it's odd, we're going to pass through the x-axis. When it's even, we're going to touch or turn around. Let's get back to OneNote. Boom. So once again, it's always a good idea to just knock out this chart and get the answer. All right, the answer here ends up being x is contained in. Oh wait, let's get that real quick. Do we include 0 and 1/3?
No, because we have a strictly greater than symbol. We don't have a greater than or equal to.
Put big holes there. And we want when it's positive or negative.
We want positive.
Right? We want when this graph here, this one-dimensional graph, is describing the left-hand side. So when is the left-hand side, when is this graph bigger than 0? That's everything from 0 to 1/3, and everything bigger than 1/3, but not including those two numbers. So 0 to 1/3, not including them, and then 1/3 to, for everyone who cringes at my infinities, there's a normal one, to infinity.
Not beyond.
And beyond, like Buzz Lightyear. Oh, I love Toy Story so much. Okay. So, just like getting this graph out and checking numbers, always a good idea. Foolproof. It's going to work every time. But if you start to think about what this graph looks like, it can lead you to making intuitive answers before you even solve it, which is kind of a goal here. We want to see the math and see how the geometry compares to the algebra. So here we have our answer. All right. Rational inequalities. This drives people insane. Solve the inequality below. What do you want to do, Mrs. Contreras?
Well, we have a 0 on one side, so that's good. We don't have to move anything around. So I'm happy about that. But I'm sad that we don't have like a common denominator on the left side. So I think we should work on that. And multiplying by x minus 1 in the numerator and denominator, so it's actually just a 1.
So you want to multiply that 2 by x minus 1 over x minus 1?
I think so.
Okay, so let's go ahead and do that. X minus 1 over x minus 1. Cool. Go ahead and put parentheses there because that makes me happy. This is greater than or equal to 0.
Still greater than 0. And then we can simplify it a little bit.
Simplify. So 3 plus, I'm going to go ahead and distribute. Minus 2.
Sounds good.
All over. And I'll write the final line in a second. X minus 1. Strictly greater than 0. And then the final line is going to be what? 2x plus 1 over x minus 1. Let me go ahead and scroll down a little bit. Is strictly greater than 0. All right. So what do you want to put on our number line this time?
Well, we have like two, I guess we can call them important points. We have where our denominator equals 0, which is at 1, because that's just where that graph is going to break if we were graphing it. And we should also probably use what, -1/2, because that's where we have a 0 in the numerator.
Let me just go ahead and just do the math. All right, solve that one for 1. That's the one we got. And then this is going to be -1. And then 2x is equal to -1. Divide by 2. X is equal to -1/2. Cool, right? Does this graph change from positive to negative at 1?
I don't know.
Let's find out. Let's plug things in. So if I plug in something less than -1/2, like -1,000, I'm going to get a really, really negative number, -2,000 plus 1, divided by -1,000 minus 1. That's a negative and a negative. A negative divided by a negative, which ends up still being a positive. Cool. All right, when I cross -1/2, I'm going to have to plug in something between -1/2 and 1. That's annoying. Is there a number between -1/2 and 1 that exists that's easy to work with?
Yeah, totally. 5/7.
All right, 5/7. Let's do 0 instead.
Oh, yeah, okay, that sounds better.
Yeah, so we got 0 plus 1, 1 over -1. 1 divided by -1, that's going to be a negative number.
Mm-hmm.
What happens as I cross over 1? And I want you to, I don't want to plug anything in. I just want you to think about this. As I go from, let's say, negative point, or 0.9999999 to 1.00001, when I cross over 1, what's happening in this expression? Is anything happening to the numerator in terms of its sign? It's SIGN?
No.
No, right? It's going from positive to positive, right?
Still positive, yeah.
Is anything happening in the denominator?
Well, that'll change. Right?
That'll change, right?
Yeah.
That's going to go from, I think, negative to positive?
Positive. Mm-hmm.
So when I get to these critical points, that is precisely when each factor in my left-hand side expression is changing its sign. So when I get to -1/2, the top one's changing its sign. When I get to 1, the bottom one's changing its sign. So every time I get to one of these critical points, I'm changing my sign. Right? There's one exception. And that's, let me scroll up, right here. When I get to 1/3, my sign didn't change. Plus stayed plus. But that's because I'm going from positive to positive. Right? Whenever you have an expression that doesn't have an even power, in this case, both of these have a power of 1. When you get to that critical point, you are changing signs. So we're going to go from positive to negative to positive. So technically, once you get this one right here, you can just alternate. Right? When do you not alternate? When you're given something with a square, or a 4th power, or a 6th power, or an 8th power, etc. All right, so I do not believe we're done with this problem. Right?
Right.
We want to just write our answer out. We're looking for when it's positive, right?
Mm-hmm.
Right, so it's positive from -infinity to, see, I don't like writing that. It doesn't feel good. -1/2. And are we including -1/2?
No, because we're using strictly greater than.
Awesome. And
but if we were having greater than or equal to, then we would have a square bracket. But for 1, we wouldn't.
Right? Why wouldn't we though?
Well, because if you plug in 1, then don't you get an undefined on one side? So then the whole thing breaks.
Yeah. So regardless of what if this is greater than or equal to or strictly greater than, right, the denominator, when this expression is undefined, it's going to be a whole every time. All right. So we got, and then what do we got? We got 1 to infinity. I'm not a fan. I'd rather just draw 2 circles. I'm trying for everyone.
You can do whatever you want, Mr. Kirk.
True. Okay. Let's continue. Solve the inequalities below. All right. Do you want to just cross multiply?
Oh my goodness, no. I think that's a terrible idea.
Talk to me. Why?
Well, there's so many things that you might potentially lose if you just cross multiply in doing this, because whenever we multiply by a negative number, for example, across the inequality symbol, that we have to flip it. Mm-hmm. Because even though 5 is less than 7, -7 is less than -5, right? So because we're working with variables where we don't actually know if they're positive or negative, that just seems like a bad idea.
Yeah, what I want to do is if I have 1 is less than 5, that's totally true, right? That's totally true, right? 1 is less than 5?
Yeah. I nodded.
If I multiply by x on both sides, is x less than 5x?
Yeah, I know. It depends.
Right?
It depends on if x is
positive or negative.
500. Yeah.
Yeah. I mean, if x is a positive number, this will be true. Mm-hmm. But if x is a negative number, this won't be true. You would need to flip the sign. So we cannot just multiply by variables. Don't get me wrong. You can multiply both sides of an inequality by a number. And if you multiply by a negative, you just need to know to switch the sign. But when we're dealing with variables, we don't know if that variable is positive or negative. So instead of multiplying by, in this case, x plus 3 and x on both sides, let's just move the right-hand side to the left-hand side or the left-hand side to the right-hand side and never do any variable multiplication. Because if I have like 1 is less than 5 plus x, and I subtract x on both sides, right? If this first statement's valid, this second statement is valid. So I'm allowed to subtract variables and add variables, but I cannot multiply by variables in an inequality. So I'm going to go ahead and erase some of this stuff because I want the space. Let's go ahead and just subtract x minus 1 over x plus 3 minus 6 over x is less than or equal to 0. And what do we want to do? Find a common denominator?
Yeah, I think x times x plus 3 is our common denominator. So we need to multiply, that first one by x. And then our second term, we need to multiply by x plus 3 over x plus 3.
Cool. And that is a 6, not a b. And this is less than or equal to 0. All right, and then we're just going to proceed, like we did before. So we got, over here we have x squared minus x minus, and I'm not going to be silly this time. I'm just going to write the correct answer, 6 x minus 18.
Nice.
All over. X, there should be a,
You just left out x in the previous line, that's all.
Yeah, what did I forget? I forgot x right here, right? Yeah. That's all I forgot. Cool. Yeah. I was worried there for a second. We got that? And then let's go ahead, let me see how much more room I have on this page. I got a little bit more room. Here's the textbook section where the material we're talking about. All right, x squared minus x minus 6 minus 18, that's going to be x squared minus 7x minus 18 all over x times x plus 3. And then this factors, right?
Yeah, that factors. I think that's
9 and 2?
9. Yeah.
So x, what's going to be a minus 9 and a plus 2, as you said. Alrighty. And we are less than or equal to, let me make sure that's obvious, 0. And that's an x. And then what are we going to do here? We just want all these critical points, right? These are the points, 9, negative 2, negative 3, 0, where our graph switches sign, right? Our graph is going along. When it gets to, I think the first one here is negative 3, this expression goes from negative to positive. Or it goes from something to something. Let's establish this first one. Let's plug in like negative 1,000. Okay. It's going to be a negative times a negative divided by a negative times a negative, right?
Positive.
Which is a total, at the end of the day, a positive. When I get to negative 3, my graph's going to, this expression right here is going to go from negative to positive. So I could draw it if I want. All right, but that, a negative times a negative divided by a negative times a positive, that's a negative. When I get to negative 2, this expression becomes positive. So I'm going to switch sign. And then when I get to 0, this is going to change from negative to positive. So I'm going to change sign. And then when I get to 9, this is going to change sign. It's going to go from negative to positive. I have my little chart here. Wow. We don't always have to just plug things in. We can also use this knowledge that we're changing sign at these pivotal points.
Pivotal points.
Ooh.
So we keep on using different words for describing these. Is there like a technical term we should use? Because I know that critical points is something that we talk about in calculus, which you can Google if you want to, but we will not talk about in this class.
I think critical values is valid, right?
Well, critical values, that has a very specific math definition.
What is its very specific math definition?
That's when the derivative equals 0.
Okay. There are students watching this video right now that are getting really excited. The derivative is equal to 0. Interesting. All right, let's call these points.
Like points of interest. We could call them.
Yeah, let's call them points of interest. And then if I forget, yell at me. Let's call them points of interest.
It's the calculus seeping in to the pre-calculus. That's what's happening.
I got you. All right, so we are x is contained in. We are strictly less than. No, we're not. We are less than or equal to. So we
Then
are
it looks
going
like we can
to
use
include
closed
negative
bracket.
3?
No,
Why not?
because -3 makes our denominator 0, and so undefined is not something that we can handle.
Yep, and then the same thing at 0, right? But we
Correct.
can include -2 because our graph will be 0. And we can't include 9 because our graph will be 0. And feel free, everyone, to go to desmos.com and graph what we've started with here, the left-hand side, and then see what this graph does. It's pretty interesting.
It's really pretty, actually, because if you do it with the inequality, then you get like the dashed and the solid lines. It's really pretty.
So we want that, we want the negative stuff, and we want the negative stuff, and we're going to be left with -3 non-inclusive to -2 inclusive, union, 0 non-inclusive to, let's ignore that page number, 0 to, what is that going to be, 9 inclusive.
Cool.
Sweet. Excellent.
We should do like a Desmos art project.
I'm 100% down for that. But now that we've said it on this recording, we have to do it. I mean, we've committed to this. All right, let's proceed. All right, this is when inequalities start to get, in my opinion, mildly difficult. All right, before, what have we done so far? We talked about notation on this first page. Then we started to factor, and we started to use these charts to establish when the graphs are negative and when the graphs are positive. At this point, we started dealing with denominators and when the graph is undefined and not undefined. Those points of interest in the denominator are still valid for when the graph is changing sign, but they are not actually when the graph is 0. Inequalities, that is when it starts to get interesting. So, looking at this equation right here, absolute value of x minus 2 is equal to 5. What do we need to think about?
Well, we need to think about both the positive and the negative times, or the positive and the negative, I guess, values for what that left-hand side could be, so that it equals 5.
Right. I think there's only 2 things that when you take the absolute value of, you get 5, right? What are they?
Yeah. Was it 5 and also -5?
Right. We need this thing right here, inside of the absolute value, to either be -5 or 5. Right? We need x minus 2 to be -5, or we need x minus 2 to be 5. But I think there's a more important way to think about this. I'm going to go ahead and erase what I've written here. I want x minus 2 to be equal to 5. That would be valid. Or I want the opposite of x minus 2 to be equal to 5. The way I like to think about these problems is I want this thing inside to be, I'm actually starting to have a brain fart. I'm rambling.
Okay. Do you need help?
Kind of.
Well, so we have x minus 2 equals 5. That's pretty clear, right? That's like 7. That's not too bad. But then when we have negative quantity x minus 2 equal to 5, that is technically like the same as saying x minus 2 equals -5, right? If you just divide out by -1. But this just seems like a more elegant way of talking about it. It is kind of personal preference, I think. But this gives us the idea that our absolute value is actually like a plus or minus of the expression equals an answer, which gives you also the expression equals minus or plus of the answer.
I like that. Plus or minus x minus 2 needs to be 5 for this statement to be true. So we have these 2 equations. If I add 2 to this one, I get 7. If I if I divide by -1, I get x minus 2 is equal to -5. And if I add 2, I get -3. Both of these work, right? If I plug in 7, I get 7 minus 2, which is 5. The absolute value of 5 is 5. And -3 minus 2, that's -5. I get 5. All right, over here, we need x squared minus 6x plus 4 to be 4. But we can look at when the opposite of x squared minus 6x plus 4 is equal to 4. those are going to be our solutions for this inequality. No, sorry, not inequality, this absolute value equality. All right, so now we just need to do this. If we subtract 4, we get x squared minus 6x is equal to 0, factor, and we get x equals 0 and x equals 6. And then down here, divide by -1. We get -4. We add 4 to both sides. Let me scroll down. We're going to get x squared minus 6x plus 8, which factors? I believe it factors to -4, -2.
-4, -2, yep. So,
right, so to add to our solution set, we have 4 and we have 2.
That's tight. Because they're also, it's like 0, 2, 4, 6. It's
0, 2, 4, 6, ascension.
It's nice.
Sweet. And we can also double check 0. Let's see. We get 0 minus 0 plus 4. That's 4. Wonderful. If we plug in 6, we get 36 minus 36 plus 4. That's 4. If we plug in 4, we get, what is that, 16 minus 24, which is -8 plus 4, which is -4. So the absolute value of that is 4. And if we plug in 2, we have 4 minus 12, which is, once again, -8 plus 4, which is -4. And its absolute value is 4. All 4 of these answers are valid.
Nice.
Let's go ahead and scroll down. Let's make it really hard. Let's start looking at absolute value inequalities.
Oh, boy.
Okay. So how can we interpret this sentence, this absolute value of x minus 2 is greater than 5?
Well, we could think about the difference of x minus 2. The magnitude of that is more than 5.
So x minus 2, we want to make sure that that thing is more than 5.
Mm-hmm. But that also means, with our plus or minus understanding, that negative of x minus
needs to also be greater than 5, right?
Right.
If we plug in I don't know, -10. -10 minus 2, that's -12. Negative times -1 times -12, that's 12, that's greater than 5. We're looking for things that when we subtract 2 from them, they're greater than 5, or the opposite is greater than 5. Right? We can have very negative numbers here, because those will be greater than 5. Right? This is an or question. Right? Either of these can be true in our final answer. So let's just go ahead and solve these, right? X needs to be greater than 7, or I'm going to divide by -1 on both sides. What do I need to do?
That's dangerous, right? You got to flip the sign, because once you're dividing by a negative, your inequalities changes.
Excellent. So then we're going to add 2. We have switched our sign, and -5 plus 2 is -3. And we have x is greater than 7, or x is less than -3. So I believe we can just go ahead and say our final answer is x is an element of, what's the interval notation here?
We need a parentheses, -infinity, comma, -3, parentheses.
-infinity to -3, parentheses.
Union.
Mm-hmm.
And then start at 7, and then we go to infinity. And yeah, we're not including 7. Or infinity. We can't put a bracket on positive or negative infinity, right?
Like ever, yeah. And we can just double check our answer. Let's plug in something like -10. As we checked earlier, that worked. -10 minus 2 is -12. And -12's absolute value is in fact bigger than 5. And then same thing for numbers larger than 7. All right, both of these two intervals work.
Nice.
All right, so let's look at this one. X plus 6 needs to be less than or equal to 3.
So that means that the plus or minus version of x plus 6 needs to be smaller than 3, or within this 3-sized bubble.
Yeah. So let's think about that. We need this thing to be within what interval? When we plug stuff into this, what interval does it need to be within?
between positive and negative 3.
Let's just write that down for a second. Let's proceed through the problem, but let's write that down. All right? We need to find all the x values, and when we plug them into this expression, it's between negative 3 and 3. And in this case, we can include negative 3 and 3 because we're also equal to. Right? So let's look at now the two inequalities. X plus 6 is less than or equal to 3, and negative x plus 6 is greater than or equal to, sorry. That's what I want.
Mm-hmm.
Let's look at these two inequalities. Right. So let's go ahead and subtract 6.
Mm-hmm.
And we get, what do we get? Negative 3. So x needs to be less than negative 3. And then if I divide by negative 1, I get x plus 6 is greater than or equal to negative 3. I have to switch the sign. And then if I subtract 6 again, I get x is greater than or equal to negative 9. Now we need to notice something here. Give me a number that's larger than negative 3. Like substantially larger than negative 3.
5 million.
5 million. If I plug in 5 million into this, will it satisfy this equation?
5 million
Plus 6.
Plus 6 is 5 million 6.
Oh, wait, no, rewind. I just said x is greater than or equal to negative 3. I meant less than. Give me a number that's substantially less than negative 3. Sorry about that. I rewind.
Negative 5 million.
Negative 5 million. If I plug in negative 5 million plus 6, do I get an answer that's true?
Negative 5 million plus 6 is no, because we're absolute valuing it.
Right?
Mm.
Pick a number substantially larger than negative 9. 5 million?
5 million.
5 million is still not going to work, right? It's not going to be less than 3.
Mm.
This question isn't an or question. This question is an and question.
Wow.
When we solve this inequality, we need to look at the end. When are both of these true at the same time? We can't just pick any number. We need to pick a number that satisfies both. That's not the case for when the absolute value is larger than a number. When it's larger than a number, it's an or situation. And when it's less than a number, it's an and situation.
Could we also say that this inequality is describing like numbers that are within 3 distance away from negative 6?
I think that would make sense. I'm having a hard time understanding what you're saying, but
because like
hopefully
x
some people do.
6, that means that like we're zeroing it out at negative 6.
Oh, yes, we're changing the origin of our number line.
So it's like a shift.
Yeah, we're looking for within rather than outside of, right? This is an outside question. When are we outside of 5? This is when are we within 3? There's a clever way to remember, to know if it's an or an and situation. I learned this last year. I'm just gonna do it on the side here, right? But if you draw an inequality, you can write the word and within the less than symbol and get an ice cream cone. Right? In a greater than symbol, you can write the word or within the inequality and get an ice cream cone.
Mm-hmm.
But you cannot do that the other way around. If I give you a greater than, you can't write and within it and get an ice cream cone, which is sad. And if I give you a less than symbol, you can't write or within it and get an ice cream cone. So you kind of get like an ice cream cone with like a spoon in it, but you don't get an ice cream cone. If you need to remember which, if it's an and or an or situation, either to think about it logically, which is I think what we encourage you to do in the first place. Right? This is an outside question, whereas number 2 is a within question. Right? But a fun way to remember if it's an and or an or situation is, can you write the word inside of the symbol and make an ice cream cone? So looking at number 3, is this an and or an or situation? You can think about it 2 ways, logically or with ice cream.
Ice cream, it's an or.
It's an or, right? Because if we have the symbol here, we can put an or inside and make an ice cream cone. Right? This is it's only a 1 scoop ice cream cone. That's kind of unfortunate, but it's still an ice cream cone nonetheless. Right? So this is an or situation. But the other way you can think about it is
I
logical.
only handle single scoops. Double scoops is too much. I can't do it.
I need a double scoop. What was I saying? Or you can think about this logically. This is when is the number outside of -1 to 1? It's an or situation. Right? If I had flipped this sign, it would be when is the number between -1 and 1? It's a between question. It's an and question. So let's go ahead and do it. All right, this is an obnoxious problem, but we need to know when x squared minus 5x plus 5 is greater than or 1, or when is a negative quantity x squared minus 5x plus 5 greater than 1. And I think that this video is getting long enough. We will leave this problem, I think, for the viewer. What do you think?
Exercise to the viewer.
Yeah. Find out when this inequality is true, which we've done several times now in this lesson. Find out when this inequality is true. And for this problem, as Ms. Contreras has established, is an or answer. You're going to look at when is this or this true. It's going to be a large set, whereas opposed to and, where it'd be a more constrained set. All right, I am tired. It's been a long week. You ready to close this thing out? How are we going to do it?
Favorite ice cream?
Favorite ice cream? Vanilla.
Wow.
Here's why I like vanilla, though, and I was telling some of my classes this, but vanilla is my favorite ice cream because, first of all, it tastes pretty good in the first place by itself. But vanilla, I think, is the best ice cream to add things to. Chocolate syrup, some sprinkles, cherry on top. I don't know, that doesn't feel the same when it's like chocolate or Rocky Road, or cookies and cream is pretty great, but that's basically just vanilla ice cream with cookies in it, which you could just do on your own with vanilla.
I like Oreo, coffee Oreo, when it's those combined. It's delicious.
So you just do that with vanilla. You could take vanilla, put some Oreos in it, and then pour coffee over it.
But then it's an affogato, and it's not the same.
Is that a thing?
Affogato, yeah. It's like you get gelato and then you pour espresso on top.
Oh.
Wild.
That's my favorite ice cream.